I'm Divya Chander. I am a neuroscientist. I'm an anesthesiologist. And I use the operating room as my laboratory to actually map brains as people move through altered states of consciousness. So what I'm going to talk to you today about, how many people have heard the hype recently about using stable diffusion to mind read? Has anybody heard about this recently? All right, that's what actually motivated the talk that I'm going to give today. So we're going to start with just a little bit of a history of what brain mapping and neural decoding is all about. This is a selfie that Ramon y Cajal, a very famous Spanish neuroscientist, took in his laboratory in the 1930s. And what he did was he would look under a microscope at dead brains, sliced up brains, and he would map and draw these stunning cells. We as neuroscientists owe so much of what we do to this man. And what he discovered is that from different parts of the brain, these nerve cells have completely different shapes, completely different anatomy. And you can see these like hairy things that are kind of, these tiny little hairy things, stubby things that are sticking out. Those are dendritic spines. Those are like receiving computational input-output units on these nerve cells. And it turns out that form, computation, decoding follows function. So the shape of these types of cells has a lot to do with their computing power. Now, since then, we have come a long way. This is from the Allen Brain Atlas. They have been trying to map every single cell type in every part of the brain, both mouse and human. And then there's connectomics, the idea that we can actually map the pathways that move from nerve cell to nerve cell, every single part of the brain. And that has all given rise to a static understanding of what the brain looks like. But for actually listening to how nerve cells speak, we need a way to measure their physiology. And what you see on the right is functional magnetic resonance imaging. It's when we stick people into a magnet and we actually watch how the magnet causes blood that is holding up, basically hemoglobin that's holding on to oxygen, to spin differently than when it lets it go. So that's how we use it as a surrogate to understand which parts of the brain are active and which are silent. And there on the left, on your right, what you see is somebody wearing electrodes on the surface of their skull. This is electroencephalography. And this is a way, again, both of these are non-invasive ways of imaging the brain in real time. Now, there have been a lot of new developments. So this is a company founded by Brian Johnson. It's called Peril. And he's created a device that can actually, it's portable, and it does a little bit of what fMRI does, can actually look at changes in blood flow in the brain, but it combines the best features of EEG, which is that it's fast and it's real time. And you're going to be hearing from Mary Lou Jepson tomorrow. She has a company called Open Water, in which they are using things like basically wave and phase differences and optical imaging to actually look at activity in the brain, and they're using it for diagnostics and therapeutics. So more tomorrow from Mary Lou. But we're going to start now with this idea of what these things can be applied to. So as Daniel mentioned, I study consciousness, and one of the ways in which I do that is by comparing brains that are in differentially conscious states. So that includes things like sleeping, general anesthesia, and coma. We can ask ourselves, what do these brains have in common, and what's different about them? So this is an example of what I'll do in the operating room. I'll put a set of those EEG electrodes on someone's forehead, and I will watch their brains as they move from being awake and aware to moving through these different transitions and states of consciousness, and then I will apply algorithms, everything from spectral analysis to looking at functional connectivity, how the brain is talking to itself, to looking at its information calculating capability. And recently, actually, my collaborator, Sarah Eagleman, is our next speaker's wife. We collaborated at Stanford on this paper, and we started looking at nonlinear dynamical ways of characterizing brains that were more and less conscious using complexity measures. So then I left Stanford. And the reason I did that is because I actually wanted to apply this to the real world. And it turns out that altered states of consciousness are prevalent everywhere in the hospital. And then we saw a huge rise because of things like inflammation in the brain and delirium due to COVID. And so now I'm taking some of these algorithms and artificial intelligence to a 24/7 remote brain monitoring platform to detect delirium before it becomes a problem. Other places that these kinds of algorithms have been used, other types of altered consciousness, include psychedelics. And we're finding that if you actually map brains that are, say, under the influence of LSD or psilocybin, DMT, ketamine, things like complexity, functional connectivity, information calculating capacity. And the interesting thing is that unlike my anesthetic drugs, where I tend to decrease complexity, decrease functional connectivity, and decrease information calculation capacity, what does psychedelics do you think? They actually increase all of these metrics, almost indicating that brains on psychedelics are maybe more conscious, super conscious. They're definitely more neurally flexible. And Kernel, that same company I showed you before, is combining their flow device with another company to actually look at these kinds of functional changes, for instance, when subjects are using ketamine for therapeutic reasons. But one of the more interesting places for a long time that we've actually seen algorithms being deployed is for movement. Now, how many of you have heard of deep brain stimulation? Great. So for those people who have movement disorders, things like OCD, depression, you can actually implant an electrode deep into their brain, and then you can kind of tunnel the battery pack under their collarbone. And this is the place you can change out the battery, and you can also program different stimuli. And it turns out that many of these devices have different characteristics. Their electrodes are in different places. And this enables them to do things now like closed-loop DBS, where you can actually get behavioral input from the subject, you can read neural activity, and then you can deliver and titrate current into the brain based on these closed loop systems. And what you can see here in this video is a Parkinson's patient who basically, we're going to start with the stimulator off, and you're going to watch his left hand, and you'll see that it's shaking a lot as he tries to transfer water from one cup to the other. So again, this is the off state. The stimulator is not on, even though the implant is there. And then it's going to get turned on. This feedback loop is going to take place. And just watch him try now with the DBS on to actually transfer water. Same hand. If you want to see a really cool video, go to YouTube and look for the Mayo Clinic and look for a violinist having this operation done awake, and watch him actually play the violin in the operating room. All right, so movement. That was a deep brain stimulating electrode. It's actually quite large. They're very thick. This is a different example of electrodes that touch the brain. This is 96 electrodes. This is the most famous brain-machine interface, for those of you who are not aware. It is a Utah array made by BlackRock Technologies, and the smaller version of it is about the size of a baby aspirin. And these electrode arrays sit on parts of the brain, in this case the premotor cortex or the sensory cortex, and they capture information coming from an individual who may be, for instance, paralyzed, captures their intent to move, and again, deploys artificial intelligence in order to help them move. And it sends this information out to an actuator. Now, this is an older video, and it's important to set this up. This is from the BrainGate consortium. This woman has one of those implants in her brain. She cannot move from the neck down. And she's using her mind to control this robotic arm to bring a carafe of coffee to her mouth so she can take a drink. It's pretty extraordinary. Now, this is the guy who gets all the hype, right? Elon Musk. So Neuralink, yes, it was founded by Elon, but his co-founders and a lot of his board members are actually people who are from the BrainGate consortium. And so he didn't invent this technology, but he has made improvements. For instance, because they've got a lot of funding, they can do things like, instead of the sharp metal electrodes, they've been able to create electrode threads with higher packing density, make wireless systems, and make systems that can actually calculate and compute faster. Now, this did not get FDA approval this month to start human clinical trials. By the way, one of the issues that the FDA wanted to address is what the effect of a lithium-ion battery would be inside someone's brain. The second problem they were concerned about was overheating. So there are a few things to worry about, but they're going to make some progress. Also, electrodes can damage the brain when they touch the brain. And that's why we have non-invasive technologies for decoding and motor. This is a gentleman who is paralyzed from the waist down, but he has an EEG device on his head, and when he imagines he wants to walk, that signal gets decoded by an algorithm, sent to this exoskeleton, and it helps to move his legs forward like this. And by the way, he also trains in virtual reality. We've had a few sessions on that, and we'll have another one. And that feedback actually has enabled some of Miguel Nicolelis's patients to regain neurological function without any surgical intervention. Moving in the non-invasive space, that is a myoelectric band. That is something that also senses the intention to move, say by an amputee, and these muscle activations are picked up by the band and sent to a bionic arm. And then a few years ago, I was at Augmented World Expo in Silicon Valley, and I saw this device. It's from a company in Israel. It's a band that doesn't measure muscle activations, it measures the intention to move using neural activations. And what they've done is they've moved it into the consumer space. You can see somebody having attached the motor device to an Apple Watch to actually turn it into a gesture controller. So this device is now training specifically on these different movements. Let's move on to vision. Reconstructing visual experiences. This is also an older video, but there's a reason I'm showing it to you. One, it's the first example of using algorithms to read the mind during vision. The second is, take a look at the first author, Shinji Nishimoto. He is the postdoc who did this work in Jack Gallant's lab at UC Berkeley. And the work essentially involves putting a bunch of students into a scanner, an fMRI machine, and presenting YouTube video clips to them, recording activity from the back of their brains, and creating a data dictionary. So basically, all the statistics from this first part of the visual system were being compared to the statistics in the images. And by doing this, they were able to reconstruct pretty grossly what that person was seeing. Now, that was in 2011. And in 2013, a group of Japanese scientists in Kyoto tried to do something very similar to map the semantic content of people's dreams. All right, let's fast forward. This is at the end of last year. This is the first example of using generative AI to do this kind of visual decoding. So this is not the study that got a lot of press, but essentially this particular model, you can see the ground truth. Basically, the objects that the subject was looking at are in that column on the left. And the algorithm reconstructed it on the right, that's the thing in red, and you can see that it outperforms any prior algorithm. And the one that hit the press, this is not even a published paper, it's actually going to be presented at a computer vision meeting in 2023. But this is the one that used stable diffusion. And it does a better job than these prior algorithms for a couple of reasons. What you see there is the ground truth on the left-hand side. That's the image that the person was presented with. What's in the Z column is that exact part of the brain that was being imaged in Jack Gallant's study, so area V1. So it's the first part, and you can see it kind of generally captures color and the position of objects, but it doesn't do a very good job in reconstructing exactly what the object was. C, higher visual area, like further in the visual stream. Parts of our visual stream are associated with semantics, the sense of what it is we are seeing. That is where the latent diffusion model comes in, because what it's good at is converting text to image. Has anybody played with these, like DALL-E or, right, exactly. All you do is you give it a text prompt and it generates images. And the end result, when you combine these two things, is something that looks a lot more like what the subject was presented with. Again, on the extreme left, on the extreme right. Now, this has been taken into speech as well to create assistive devices for people who have lost the ability to communicate. Some of the very first studies use that same Black Rock, Utah array in the motor cortex so that people who could not speak but could imagine typing using a mouse could imagine typing out sentences. Since that time, so in 2019 at UCSF, a group in Ed Chang's lab, he basically started his life as a functional neurosurgeon, which meant that he would often do surgeries to remove areas that were doing things like causing seizures. And because he had these electrode arrays over the brain to map the areas of seizure focus, he decided to start doing some recordings. And in one case, he wanted to see if he could reconstruct what somebody was imagining speaking by having them imagine moving their mouths, or to move their mouths as if they were saying something but with no sound coming out. And you can see that reconstruction here. So this is actually motor to speech, and that is the vocal apparatus creating some kind of sound. There's sound on this one.
Is not available in books.
The proof that you're seeing is not available in books.
That was synthesized by imagining the person's mouth moving. Again, in 2021, a step forward was made where a person who needed to communicate could imagine writing out what they wanted to say, and that was reproduced in synthesized speech. And this was one of the fastest demonstrations yet, up to 90 characters per minute. And again, another company, this time Peril, they've kind of beaten Neuralink to these sort of large-scale cortical recordings, and one of their very first clinical uses will be as an assistive communication device. So let's move to hearing. I don't know how many people know this, but the very first brain-machine interface was a cochlear implant. And when we would screen infants and newborns to see whether or not they could hear, if they couldn't, we would immediately try to get a cochlear implant into them because of the plasticity of the brain. Well, that has also gotten more and more sophisticated. This is research that was just published the end of last year by Meta. And Meta has their own AI division. And the reason this is so interesting is because a lot of what I have shown you is using sophisticated algorithms to decode what the brain is thinking, intending, wanting to do when electrodes touch the brain. This was done non-invasively. This was done with electroencephalography and magnetoencephalography. And what they found is that they basically had subjects listening to audiobooks, and they were able to reconstruct using the magnetoencephalogram. They were able to correctly predict the sounds that they were hearing 73% of the time. So that's very unusual. And again, non-invasive, this opens up an entirely new world of possibilities. And just a month later, this was actually, whoops, that has a video. Are you able to help me play the video? This comes out of the University of Texas at Austin, and Jerry Tang's the first author. And essentially what they did was they had people either imagine speaking or watching silent movies, and they tried to reconstruct what it was that they were imagining hearing. And they didn't always get it right, but they did get kind of close, neck, breathing under control. So we're getting a little bit closer and closer to this. And this brings me to what Daniel mentioned yesterday, Amara's law, right? So human expectations, very linear. And right now, we're kind of overestimating. There's a lot of hype about what these devices can do. But with the direction that our algorithms are going in, we will soon be able to non-invasively do so much more than we ever thought. You saw an example also yesterday with Andrew Hessel of DishBrain. This is the chip that is both in silico, but it also has nerve cells that are grown on top of it. And it learns how to play Pong. What he might not have mentioned to you yesterday is that this combination of silicon and neural tissue outperforms artificial intelligence by a lot. It only took this 15 iterations to learn how to play Pong against an AI, something like over 300 attempts. All right, so it's doing really well. All of this is to bring us to the point of understanding something very, very important. These devices have so much promise, but things like these myoelectric bands, et cetera, they're being used by companies potentially to gather a lot of data, to move us into worlds that are full of gaming and places where you might actually be able to say, use a device like this and read someone's mind and gestures. Now, this company, Neurable, tried to create a mind-controlled VR gaming device. They didn't succeed, but this collaboration did. Galea is a collaboration between OpenBCI, for those of you who have heard, it's a DIY BCI company, Valve, which is a gaming platform, and Tobii, which is an eye tracking platform. And essentially, what they're trying to do is capture all this biometric data so you can easily move through a virtual space without ever having to touch a controller. And this brings us to this place of neurocapitalism where information can be presented to you and read using algorithms from your face, from your brains, by tracking your eyes, often without consent, often without knowledge. Facial recognition is being added to this, and yes, we can do it with brainwaves. Imagine if you go to get a job, and they actually want to measure your brainwaves in order to know whether or not you might have, say, some kind of neurological disability, or if they might want to know if you have the potential for addiction. And this is where I think that we're getting into sort of the science fiction realm. So I want to also let you know that if you imagine typing in a password, that can actually be picked up and hacked by a non-invasive brain-machine device. We can also create fingerprints using your brain, so brain prints, that can detect your brain with 100% accuracy, completely non-invasive. We have troves of data that can actually analyze, using non-invasive data, what your mental predispositions might be, and we can digitally twin you, or we can deep fake you. We've also figured out that anything implanted, whether it is a Medtronic pacemaker, whether it is an insulin pump, or a deep brain stimulating electrode, can also be hacked from the outside. And cybersecurity is becoming a huge part of this entire brain-machine interface market. Finally, we have actually learned a little bit about how to create false memories and potentially implant them through stimulation because we've been able to decode what's going on. And this is where I want to leave you with this idea that protecting people's both genomic rights, as Jamie was talking about yesterday, and their neural rights is a really important thing. I was just down in Chile. I don't know how many of you know this, but Chile is the first country in the world that has actually passed a law protecting people's autonomy and agency so that their brains cannot be read from or written to without their consent. So with that, I will leave you. Thank you so much for your attention.
Thank you, thank you, thank you.
Oh.
Mind-blowing. Super, you are mostly on reading the brain. What's your quick synthesis of where we might be in a decade writing to the brain?
Writing to the brain is easier to do when you have invasive electrodes, right? However, we are finding more and more that you can use things like focused ultrasound and even transcranial electrical and magnetical stimulation to get to deeper brain structures. And I think that now that we've been able to decode so much, we'll actually be able to start rewiring nervous systems, especially for mental illness and things of that nature.
Right.
So.
All right, thank you, Divya.